I'm really excited to be here today talking to you about trust agility in era of transient ties, particularly in the context of TLS trust and why we need to rethink that. Centuries ago, we lived in a world where our friends, neighbors, and the people we did business with would mostly remain the same for a long period of time, often throughout our lifetime. This made building and maintaining trust easier. As societies have become more transient, so have our ties. And this trend has not only continued, but accelerated online when we need to continuously renew trust. This demands trust agility. This is the ability to continuously and rapidly redefine trust relationships online, and as well the emerging protocols and technologies that support this rapid evolution. I will be focusing on trust agility and what we need to make it happen. But first, let's look at some basics, particularly in the context of secure communication. When you're using a browser or any internet connected device for that matter, how do you know you're talking to the designated server, for instance, Netflix? Now, browsers have done a tremendous job making it inherently difficult to visit an insecure website. You would see a huge warning that prevents you from proceeding. You can still inspect the connection. You can, for example, review the service certificate being served by the server. This certificate is exactly what's making the authentication of the server identifier or the application ID possible. In this particular example, via DNS name, netflix.com. In other words, the certificate is a trusted association between the certificate, between the server identifier, a DNS name in this example, and the cryptographic keying material that is in control by the server. Now, this particular certificate is issued by a public certificate authority, or for short CA, and public in this context means that the root certificate is by default trusted by browsers. And we will be talking in a moment what that entails. However, for the purposes of this talk, we will leave aside the technicalities related to domain validation that usually needs to occur before the certificate issuance, sometimes per each certificate issuance. Outside of browsers, we are facing the same challenges of secure communication and establishing trust, whether it's a TV, a console device, or a mobile application. In these environments, the server can opt in to serve a certificate from a public CA. Alternatively, a private certificate authority can be used. Now, private in this context means internally operated by the enterprise, where the root certificate is not automatically trusted by browsers and systems out there. So the root certificate needs to be distributed and installed in advance, something that's feasible if the organization is already building client applications. One of the key messages of this presentation will be on the shift from public to private trust where it's applicable, and we will be talking about that more. But first, let's look at a root certificate from a certificate authority. On its own, this is a self-signed digital artifact. It doesn't have any power, right? You can go and take it and issue a service certificate for a host name or an IP address. If you present it to a client, the client can look at the digital signature, verify it, make sure it's issued by the root CA, that it's not expired as well. But ultimately, it boils down to the fundamental question, should I trust this root certificate authority? And trust only comes into play if the root certificate is already pre-installed on the trust door of the client. And this is a bit behind with the slide, sorry. And this is where trust anchors come into play. When you install a browser or an operating system, it comes with built-in trust door. And this is a collection of basically a list of root certificates. And these trust stores are managed by trust programs by a few organizations out there that they operate their own trust store in each individual domain. So if a root certificate, if it's included in a trust program, it will be by default trusted by the respective browsers and operating systems. Otherwise, it will not be trusted. Now, each trust store has a well-defined inclusion process outlining the policies and the technical requirements that a CA must meet to be trusted. All browser trust stores as well need to enforce the baseline requirements defined by the CA Browser Forum. This is a group of representatives from CAs and browsers come together and define these requirements. CAs as well undergo regular audits and ongoing due diligence to ensure continued compliance. If they fail to meet these standards, there is a risk that they can be excluded, an event that we call distrust, and this can happen from time to time. Some trust stores, particularly Mozilla, are accompanied as well with a public aspect to them, where there is a public forum and anyone can follow conversations and discussions, or as an expert, you can as well contribute to the conversations. Now, the web trust infrastructure has evolved significantly over the last 2 decades. The first generation of roots were generated and minted in the mid-90s and early 2000. Many of these were valid for up to 30 years and trusted throughout their lifetime. And we are already experiencing the first wave of expiration of these roots. Some of them are causing some ripple effects given how deeply they were trusted in the ecosystem. At the same time, many of these certificates were issued using cryptographic primitives and algorithms that are no longer meeting the standards of today. Some of which, such as MD5 or Shafagh, are even considered deprecated. So the new CA term limit policy that is being introduced by trust store programs is designed to address this issue by limiting the active lifetime of roots to 10 years on these trust stores. This ensures and facilitates cryptographic agility. This is the ability to seamlessly move away from deprecated cryptographic algorithms. And this will be the first major cleanup of these older roots from the trust stores. This started in 2025, and it will be concluded by 2029. And by that time, there will be simply no roots that have been present for more than 10 years. While this is great from the crypto agility perspective, particularly for the browser ecosystem, which has a faster cycle in terms of getting updated, it poses some significant challenges for constrained devices that have a slower update cycle. And this is where we need to carefully navigate some complexity that we will be talking more in a bit. But first, I would like to highlight another important change with respect to the maximum server certificate validity that has been shortening over time. In the early days, there was no well-agreed or well-defined maximum validity for server certificates, so they could be valid for different periods. If you wanted to change the format of the cryptographic algorithm, one would need to either revoke all the impacted certificates or wait for them to naturally expire, which would be a very long time. So to address this, the CA Browser Forum introduced a maximum certificate validity, at the time 5 years, and this has been over time ratcheted down, and we are currently at maximum 1-year certificate validity. However, we are over the next few years heading towards a maximum validity length of 47 days by 2029. Now, what are the implications of these changes, particularly the CA term limits? One major consequence is an increased device fragmentation due to rigid trust assumptions. In practice, this means older browsers and devices, they may no longer recognize the latest server certificates. You will simply see the error message that's preventing you from proceeding. There are workarounds to extend trust to legacy devices, but these solutions come with significant complexity for server operators. And these are the challenges we need to address as an industry. To illustrate device fragmentation, let's take a look at the Android device ecosystem. Today, based on historical data, it takes roughly about 10 years for a new Android release to go through its peak of roughly 30-35%, and then gradually slowly fall below 1%. And you can see that illustrated in the image on the right side. You don't need to look at the versions, just the colors as they're getting introduced. And as you go towards the right direction, the population and fraction is getting smaller and smaller. So now consider that trust assumptions today on operating systems are rigid. The trust store is typically immutable outside the OS itself. And for most users, this means root certificates cannot be updated independently of the OS. And this is specifically problematic in certain regions of the world where hardware limitations prevent the users to update their devices. Now, to address this, Android has introduced updatable trust stores within Android 14. However, given the decade-long adoption curve, it will likely be 2033 before updatable trust stores are available on more than 99% of Android devices. So we need to start acting today to prevent being impacted by device fragmentation and to manage the complexity of our solutions. And the way forward is move toward greater trust agility. So I would like to share our journey on this path. At Netflix, we have been heavily investing in automation to eliminate any remaining manually managed certificates. While there is still the long tail of manual use cases out there that we need to get in front of them before we reach the 47-day maximum validity length, we are making strong progress. We are also strong advocates of short-lived certificates and are moving our ecosystem towards them. Short-lived certificates, as defined by the CA Browser Forum, are 7-day valid certificates, and what I like most about them is that they don't even include revocation information in them, making them more compact as well in size. This approach comes with significant resiliency against certificate revocation events, which are more common than many realize. For example, in the event of a security incident, you might get a 24-hour notice or 5 days for non-security incidents to go and then rotate the impacted certificates. Without automation, manually identifying and rotating all impacted certificates in a large organization is almost impossible. And by using short-lived certificates, we are inherently protected from these type of scenarios, since certificates are automatically and programmatically rotated around the clock. This dramatically reduces both risk and operational burden of mass revocation events and removes the need to rely on certificate revocation or even build one for our internal private CA ecosystem. Certificate revocation is also mostly considered broken because many clients and browsers out there fail open or do not reliably check the revocation status of these server certificates, allowing them to linger around for some time after they're even being revoked. Now, with automation as our foundation, we can achieve true CA resiliency by automating issuance of certificates from multiple CAs. This is increasingly important as certificate lifetimes is getting shorter. We talked about it a bit, meaning any CA availability issues can have much bigger impact on operational or even customer impact. Also, there is as well the great risk of root CA distrust, which is not common. And as a matter of fact, over the last decade alone, I think we have been witnessing more than 5 major distrust events. So to mitigate against these risks, server operators need to first identify which roots are relevant for the device population with CA time limits in mind. What are the roots that are no longer trusted? Which are the newer roots that are becoming more relevant? And then attempt issuance from multiple CAs. You can use different strategies, setting up a round-robin fashion, or at the same time, you can as well have the main CA to be the default one and configure backup CAs that come into play if issuance has failed. One of the most effective long-term strategies now is in order to address the CA time limits and as well the ongoing evolution of web trust infrastructure is to separate trust boundaries. In particular, there is no need to rely on browser-trusted routes whenever browsers are not even part of the equation. More specifically, when you're looking at the machine-to-machine communication pattern. For example, consider the generic endpoint of logs netflix.com. If this one is shared across mobile apps, browsers, and TVs, we are forced to maintain a single common trust assumption for all these device platforms. And as Web trust ecosystem is evolving, this becomes increasingly difficult and very risky. So by moving to dedicated platform-specific endpoints, we can tailor TLS configuration for each of these use cases. This allows us to distinguish between public and private trust. As you have new device populations getting released, you can move gradually to private trust. At the same time, you can maintain endpoints for legacy use cases where trust assumptions are different. And ultimately, this reduces operational complexity and risk that comes with shared trust boundaries. As you can imagine, it's really unrealistic to expect every developer and service owner to fully understand and navigate this new level of operational complexity around trust and certificate management. So to address this, we have found using templates for certificate issuance an effective way to abstract away the underlying details. These certificate issuance templates have intuitive, human-readable labels, such as consumer TV versus consumer mobile, or even consumer browsers versus enterprise workforce browser, making it easier for teams to select the right configuration for their service. Now, behind the scene, each template is mapped by a TLS trust expert to the appropriate root certificates and an issuance strategy that meets the platform's needs. This means developers do no longer need to worry about, should I use Let's Encrypt, a different older root, or even a private trust anchor? The templates takes care of these decisions for them. For example, looking at the enterprise browser template, it can be configured to issue the service certificate from the root X1 by default. If it fails, fall back to Y2 or Z1 in case of ability issues specifically. Now, the root selection happens in accordance with the respective audience, and in this case, the enterprise browser can be configured in such a way to use the latest roots because we can make assumptions about the audience running the latest OS and the latest browsers, in contrast to the consumer browsers where some members might be still using legacy devices. So this approach simplifies operations, reduces risk, and ensures consistency across our organization. However, the future of trust is dynamic, where trust should be actively negotiated between clients and servers. To enable this, we need a mechanism for servers and clients to communicate and agree on which trust anchors to use. This is where new standards, such as the trust anchor identifiers, are making a real impact. With this approach, more specifically, the server advertises the root certificate it supports. For example, using the same examples as before, X1, Y2, Z1. Now the server needs to make sure ahead of time to have multiple certificates ready to go issued by these issuers for the same set of host names that it's serving. Now going back to the templates, the configuration can ensure that the server certificates are issued simultaneously by all these roots and are continuously rotated and kept up to date. Now, the client can review the advertised roots and select the one that it's trusts. For example, X1, which the server would go ahead and then serve a server certificate that chains up back to this particular root. Such trust negotiations pave the path for long-term trust agility and also provide a strong foundation for adopting post-quantum roots as they become available. This means that the client can select a post-quantum root if it's offered by the server, and as well if the client supports this. So I would like to leave you all with the following. We need to start assessing the current level of trust agility in our organizations and device ecosystems. We need to invest in trust agility today to avoid negative impacts as the trust ecosystem continues to evolve. And for that, I want to emphasize the role of private trust, especially in environments where browsers are even involved. And finally, let's all contribute to the development and adoption of emerging trust negotiation standards. This is key to building more resilient and adaptable secure communication. And with this, I would like to thank you all for your attention and open it up for questions.